All right, we're back again, right? Last lecture we talked about what are the simple connection we're talking about in this class. So basically boats, there are two types, snug type, bearing type, which is A307, or you can have high strength boat, group A, group B, and group C. Last time we also talked about different type of welds, and then we briefly talk about how to calculate strength of the welds. We're not gonna require that in the exams for this class, so yeah, the information there, and you can always read, and if you really run into one. But now we're gonna talk about the both strengths, which there will be some problems in exams 3 and also in final exams, very similar, but I'm asking for really the very, very basic ones. So we're gonna talk about both strengths. Yeah, like I said, there's boats. There are two types, depending on the kind of installation method you use, and also the type of boat you can use. Snug tight, then the boat will fail in bearing, which means it will actually engage the connected parts, and then the boats will be in shear and all that. Or there's a slip critical connection where the boat will just be in post tensioning. What resists the shear force is actually the friction force. So we're gonna talk about the strength of the snug type bearing type first. Like we always say, whenever we talk about strengths, we need to know, if you want to design something, you first need to know how would it fail. So if we put two boats, use boats to put two pieces together, then I put the boat in shear, how would it fail? Okay, for the bearing type, there's two ways. The first one is the boat itself sheared off. So yeah, the boat is just a round dowel, so basically it can shear off. Another not opportunity, but another problem that could happen is the boat is too strong, but the plates it connects can get crushed at the boat hole at the boat hole edge because the boat is too strong, and typically because the plates are too thin. You could think of if you poke two pieces of paper with a pencil, then try to pull those two paper apart. The pencil is not gonna break. You're gonna break your paper. Same idea. So to illustrate this, let me kind of go to my drawing board. So two type of failure, right? The first one really, let me change it. Is you get two pieces of plate together, okay? Pull it like that in shear. Then you have a boat, right? You have a boat like right here. The first kind of failure is the boat failure, which means those two plates they're pretty strong, so you end up with like this part of your boat. Basically, if you look at the cross section, basically it's like a round cross section. It get like sheared off. How did that happen? Yeah, it's kind of something like this. I'm gonna try to do it justice, but we'll see how it goes. Yeah, something like that. The boat just, get sheared off. Boom. So you can see, like in this situation, the strength is really easy to calculate. If I know what's the kind of allowable shear strength of the boat material, then I times the area of the boat, then I'm done, right? That's the first one. The second one is something like this. You still have this situation, but now I'm gonna draw this plate to be a little thin. Okay, you have thin plates, and then I'm still pulling it in two parts, and then you have a boat that's like pretty fat and tight. Ooh, okay, well that's your boat. Oh, what's really happened? Yeah, this is really hard to draw, so I'm not gonna even try. But what happens is that at when you pull it, the boat's gonna engage your plate, and then this side of the boat gonna engage this side of the plate, and this side of the boat's gonna engage this side of the plate. But what happens is that boat is very strong, but what happens is like there's like crushing happens in the plates. So this is the second kind. So the strength of a bearing type bolt connection is really, you need to check both and then find the minimum among the two. There's no other way you can fill this bolt in shear, fill this connection in shear. So you can think about like one is yielding, one is fracture or whatever. It's like you check this one, you check this guy. There's a formula and table for that. You check this guy, there's a formula and table for that. Then you find a minimum, then that's the strength of your bearing type connection. So how do we do that? Before we do that, there's another situation where, like what I showed here, the bolt itself, I mean, if you think about it, it has a threaded part and it has an unthreaded part. So if you look at the shear plane right here, boy, I could use a different color, I think. Different width, actually, yeah. Like if you look at the shear plane here, this one, if it's gonna feel like shear this bolt off, it's gonna go through the unthreaded part of the bolt. This situation, we call it the thread is not included. We call it like N. What? Yeah. Oh, yeah. Well, we call it the thread is excluded. We call it X. Okay. The thread is excluded from the shear failure. But in this case, apparently, yeah, you can see the shear plane is going to be right here, right through the thread. We'll say the thread is not excluded. Yeah, again, I didn't write this code. I didn't write this language. I think this is like very, very confusing. But they decided to do it. They mark everything with it, so you better remember it. This one's threaded within the shear plane, so it is not, N is for not excluded from the shear plane. This one's excluded from the shear plane. So if I just pause for a moment, ask you which one, like same bolt, everything's the same, which one will be stronger? Yeah, apparently like this guy gonna be stronger. Simply because, I mean, you are shearing through a non-reduced area. Okay, so how do you actually calculate it? Stronger? Stronger? That's kind of funny. Stronger, yeah. Okay, but then you're like, how can I control it? Yeah, you can specify it. As a designer, you specify everything. And then it is a contractor's job to make sure they do it as you demand it. Of course, the price is going to be different, but I mean, like, they can always circle back to you and say, hey, that's too expensive. Anyway, so how do we actually do the calculation? If you find the formula, if you want to just calculate by hand everything, you will find the formula that is in actually J3.6. This formula is actually the first formula in J3/1 formula. The formula, like I said, is quite simple. It's some allowable stress, Fn, of the bolt material times the nominal bolt cross-sectional area. In fact, they did actually a little trick here. If you really look at this table, they'll give you different Fn for the exclude the thread versus not exclude the thread cases. In fact, that reduction should be taken on this one, right? But yeah, they're like, yeah, you know what? We're not gonna do that. We're just gonna give you a different effort. So anyway, just go by the table. You do this multiplication, then you got it. But then you're like, well, I'm gonna just use standard boats, and I don't want to do calculation. Is there a table? Yeah, you bet it. There is a table. The table is in really the nice connection tab, the boat tab actually. It's table 7/1. It's in where do they have a tab? They say a boat. Um, this one's pretty straightforward. To look at this table, you can see, okay, what kind of boat you have. Most of the time for bearing type, we're going to use this, right? But I also told you, although group ABC, those guys are high strengths, they're Flaris, but they don't always have to, do slip critical. And they can actually be installed as snug tight bearing type connectors. Just like Ferrari don't have to always go 150 miles per hour. Okay, you can drive 25 miles per hour in a neighborhood. So, depending on what kind of boat you got it. Then the N and X, yeah, that's the what do you say, thread condition. Like thread is either excluded, which actually result in a higher capacity. You see this guy and versus this guy, and not excluded, which means you're gonna share through the threads, so the strength is actually lower. This one is actually just stress, Fn. Okay, it's like right here. So you like this one actually is not that useful because you need to use this number, which is KSI, to times the area, which you don't want to do. Believe me. Okay. But what you can do is that they actually further calculate it for you depending on your boat diameter, inches. Then they calculated the area for you, okay, which is the nominal area. Then if you times this number by that number, you get these numbers. Then you're like, oh, there's two numbers. Yeah, there's a loading case, which is a single share versus double share. You guys been all doing mechanics of material, so I don't think I need to explain to you what's single share, double share. If you don't know, just Google it. A single share boat, not double share connection. So basically, if you're double share, you're having two share planes to fail, so your capacity is exactly twice. I mean, not exactly. There's some rounding things, but if you look at it, it's exactly twice as a single share. But like I said, most of the time, we're gonna stick with this guy because that's the kind of the connector you should be using for bearing type connections. Other ABC, they're probably more expensive than those guys. So you got all the way from 5/8 boats all the way to inch and a half boats. Yeah, you're saying, oh, what about I have a half-inch boat? Well, yeah, you have to do that calculation yourself. Okay, the table is just for those. But that's just take care of one limit state. If you think about that, that actually just take care of like this limit state. So now, what about this guy? Okay, what about this guy? This guy is this. Basically, if you want to get, basically there's always two ways, right? You can always do a formula calculation, a whole bunch of formulas. You just plug numbers yourself. Just read the code. It's in J3/3.10. The 3.10, that's a section name. You see, I mean, I can even list them. There's a whole bunch of formulas, but those formulas are quite easy. It is related to the type of hole, like your standard hole, short slot hole, long slot hole, and the spacing between the holes. And then if you're the last hole in the in the group connectors, then it's the edge distance, right? The distance between the edge of your hole to the edge of the plate. And also, yeah, I forgot to do there is it is related to the FU of the plate metal, which means, I see it's plate. It's kind of more general, right? If it's like a flange of a W section, then FU is probably 65 KSI. If it's the leg of an angle, which is A36 steel, FU is just 58. So if you go to this section and there are a whole bunch of formulas, you can do that calculation all by yourself. But if you don't want to do the calculation, of course, there's a table for it. Okay, the table is what it shows here. It's still in the bolt chapter or the tab. The bolt goes like this. First of all, you have the hole type. The type of hole. STD is probably what you're gonna go into is standard type, standard holes, for the most part. And then short slotted hole in the transverse direction. The short slotted hole in the perpendicular direction, that's the loading direction. The oversized hole, okay, it's oversized. Long slotted hole, da da da. Yeah, you got it. So basically, this table is for spacing. If you're in this page, I don't know which page it is, but the other side of this page is for tear out. That's where you look at for the not for both spacing but for edge distance. But here's the both spacing. You got this one, you got this one. You're like, hey, what if my both spacing is not those? For most of the standard holes, how they made it, 3 inches is a very very popular configuration. And also, if you're and then you're like, what is this 2 2/3 d diameter of my boat? What is that? This is actually if you read the code, that's a minimal boat spacing required. Those minimal, maximum spacing, those type of requirements also in the code chapter. You can just read through them. So basically, like this is a minimum spacing you can do. This is a like very popular spacing you can do. So they figure, okay, well, we'll just do those two. And then if you do something else, something in between, whatever, then you can do the calculation back to, just do it by hand with formulas. But those are typically enough because say if your both spacing is more than 3, it's 4. You pick 3 and then your number works, which means it doesn't control. Then you're all set, because the more spacing, the more of those capacities. So you got this hole type, your spacing. And then your base metal type, which is, like this one would be angle A33. This one would be like W sections. Basically, it's FU, right? Then the bolt diameter is this, and then you got those numbers. You're like, what are those numbers? Their numbers are actually the unit here. The unit is kip per inch. What does that mean? Okay, kip per inch of what? Kip per inch of the length of the boat? No. Remember, this is bearing. So it's kip per inch of the bearing thickness. Which means you need to grab this number. Then you need to times the plate thickness you're checking against bearing. Say if you're using this boat on a half-inch plate, your strength is just this number times half-inch, which is still a lot. But just remember, don't use those numbers directly. Use them, times your plate thickness. So you got this of the boat itself. Then you got bearing, you got that. Then for the bearing type bolt connection, you're all set. Okay. So what about slip critical? Slip critical, remember it's friction. So actually it's quite simpler because for this type of connection, your bolt, they're not supposed to touch your bolt hole edge because it's in pure tension, and then the friction will lock the plate together. It won't move. Uh, One kind of interesting thing you're gonna find is that in some cases, using the same diameter bolt, like say you half-inch bolt or like 5/8 bolt, you pay more to get a high strength bolt. Then you use more effort to actually post tension it. You acquire the slip critical connection. You'll find out that actually the strength is not actually smaller than the if you use that bolt just for bearing type. You're like, what the hell? Like, why after all that effort is still like a smaller capacity? Um, Actually, the slip critical connection is always more reliable because the QC on those higher strength bolts and their installation process are much tighter. And also, I think one huge advantage is that for a bearing type bolt to be able to actually engage and reach full strength, your connection need to move a little bit. Not much, you probably would never tell, but it will have to move a little bit because you have to get your bolt in bearing with your hole. But for this guy, slip critical, it doesn't matter. Once the post tension is implied, is applied, the friction is right there. It's a static friction, so you get engaged right away, and there's less slack in your connection, and it has a higher stiffness. So most of modern steel connections they use that, especially for structural connection. And also, if you have like fatigue issues, yeah, people will prefer this over the other guy. So that all sounds good. So how do we calculate it? Yep, two ways. Again, two ways. First one is you can calculate it by yourself. You just need to go to the formula. The formula for the slip critical connection is in J3.8. The section J3.8. The formula is quite simple. In fact, you don't need to remember this formula. You have the manual, but I want you to conceptually remember it. The capacity was developed from the friction coefficient. Okay, there's it's just your mu, your typical like physics friction coefficient mu, and then they can typically take two values. It is either like 0.3 or 0.5, and then yeah, you bet like 0.3 they call it a class A surface, 0.5 they call it class B surface, and yeah, apparently to get to this number you probably need to kind of do a more special surface treatment, so it's more expensive. So yeah, typically we assume it's just this. Then a factor of 1.13, that is kind of a weird factor because it reflects the fact that although those bolts they have a minimal pretension force that to be qualified as a PT bolt, you have to at least get to that PT force. But what people always do in the field is that they always overdo it a little bit. The code people they figured out that people typically overdo it by 13%. So they say, okay, well we're gonna just take this factor. Then there's a factor for failures. Like you're like, what is failures? Failures are something like this. You imagine you're gonna connect two plates together. The other plate for some reason, like here this guy's fixed, the other plate came from another place which is fixed, and then they don't met like perfectly. Yeah, if you like really crank them, they're gonna bend. So you don't want to do that. So what I do now is that you add a filler into it. Uh, Filler is just like another piece of steel. But if you think about it, if you now do a bolt through, um, it will because of the existence of this filler, and then you're doing this friction thing. Yeah, it's not too good. So they say for this filler, if you have it, um, you if you just have one filler, okay, just one, or you don't have any filler, then this will be like 1.0, okay. But if you have more than one filler, then you have to do a factor of 0.85. So basically, yeah, if you have more fillers, you're gonna get a reduction. So that's kind of a good to keep in mind because later we're gonna go to the table. The table doesn't consider that. So if you have more fillers, you need to adjust that for the filler. Then the TB is a minimal post-tension force. That is not decided by the decided by the designer. It is decided by the kind of the standard manufacturing or standard code of the post-tension bolt. Once you choose a bolt, there is a table that, in fact, the table is actually table J 3.1 table. Once you choose a type of bolt, then that's a given number. Then the single double shear, NS, you're like, oh, this friction, does it still work? Yeah, it still works. If you're double shear, to actually break your connection, they need to slide between like two surfaces. They need to break two frictional surfaces. So it's times 2 again. So now you can do all those calculations by yourself because you got this table, you got all that type of stuff. Everything's good. But if you don't want to do it, you can go to the bolt tab where there are a couple of tables. I show here is a table for group B bolts. But you can also get a group A bolts. But one thing I want to kind of really make you say this is very careful is the table is actually developed for mu equals to 0.3, not 0.5, okay. And also it is built to be don't have or only have one filler. So the filler, if you have more, you make sure you do this. But after you remember those two, this is actually very, very easy to use. Again, you have your hole type, right? You're like, yeah, what the hole type? You didn't mention like hole type have a factor here. Oh, okay. Well, if you actually go to this section, you find the impact of hole type. It is actually reflected in the phi, in this phi factor. Why they decide to do that, I don't know. But go with it. Standard hole, the phi is actually 1.0. Okay, pretty generous. Oversized and short slotted holes, phi is 0.85. For long slotted holes, the phi is 0.7. So yeah, there's a difference. Then you still have this single shear and double shear, right? And then all you need to do is just look at the bolt diameter. It's a group B or a group A. That's in another table. Then you just read, okay. You read this, 18 kips. And very, very straightforward. That's it. That's all it is. Yeah, actually the information is like right here. So for slip critical connection, there's no other limit state to check. This table and this formula, that's it. So you're like, okay, well, that is actually all you need to know about how to do boat um, strings connection. But then you're like, oh, I'm still kind of a little bit confused. Oh, okay. Though all those what I just told you is when you're doing like one boat, okay. But what if you say, okay, I have multiple boats. Say you have like one boat here, one boat here, one boat here, and then you have another boat here, another boat here, another boat here. So the code actually, when you have a situation like this, if all your force are going through the kind of centroid of your boat, and there's no eccentricity, nothing, you can assume every single boat they are the same, carrying the same amount of force. So the total force you can actually carry will be the capacity of each of those boats added together. So what you need to do is actually the following. The first one, you need to look at the boats in share, right? There's 1, 2, 3, 4, 5, 6 boats in share. Then you just grab the single boat share capacity and times it by 6. That's it. That's how much you can take if you're going to share all those boats off. Then for the bearing, it's a little bit interesting. Like for this boat, this boat, this boat, and this boat, their bearing capacity is actually determined based on the spacing of the boats. So for those 4 boats, you need to pick the bearing strengths from the spacing table. But for those 2 guys, their bearing strengths are actually determined by the edge distance. So you need to use another table. But once you did that, you can add everything together. That will be your total bearing type boat capacity. Then you compare it to the 6 boat capacity you calculated before, then you get your bearing type connection stress. And if it is a slip critical connection, then it is actually much easier because you just do this and times 6. That's it. Because there's no bearing. Okay, hopefully that will explain things a little bit. Then I'll see you next time.